So herein we'll look at a treatise of the first part of lecture 6, and it's of course with ketones and aldehydes. We're just going to briefly look at the nomenclature again and some preparations that we've done before, and then we're going to look at nucleophilic attack on the basic conditions and nucleophilic attack on the acidic conditions. Further on, later on, we'll be going through a series of named reactions and this probe some spectroscopy. So here you can see that, as we stated before, that the carbonyl is quite ubiquitous in biochemistry, etc. Because you can see here some gorgeous flavors, for example, that do have the carbonyl. So here, for example, you've got an enone attached to the benzene ring, and that's cinnamon. And then, of course, you can see here there's quite a few steroids, and you can see most of our bases, we've got some carbonyls in it as well. So you can see here, for example, I just changed this chiral center, and there's a difference. I mean, this is gorgeous, this is not. And you got some common names that you can work on. For example, if you think about it, say this fella here has got a methyl group and an isopropyl group, so of course it's methyl isopropyl ketone. And here, for example, you got carbonyl on carbon, you can call it carbon free, and well, not really, because you can say there's isopropyl here and the ethyl with a bromine on it too or something, so it's bromine ethyl isopropyl ketone. But you and I know that the IUPAC is much more precise, and so what we do is then we go about things like this. You can see that the carbonyl dominates, so of course we have a chain of 4 and there's a carbon on 2. Yeah, the carbonyl is on 2, so of course it's a 2-one. Yeah? And here, for example, we got the cyclohexanone, and of course the bromine would therefore be on 3. Here you can see that again the carbonyl dominates over the hydroxyl group or the alcoholic group, and so you can see that the carbonyl is on 2, the hydroxyl is on 4. Aldehydes follow the same theme, but of course aldehydes are always terminal, right? Of course they are. And so you can see here we got 3-methylpentanol, 1, 2, 3, yeah? And of course you can see the cyclopentene carbaldehyde. Yeah? Here, for example, aldehydes always get priority over ketones because it's terminal, so of course it's carbon 1. So of course you can see that the ketone here is on 4. We also have some names that you should be familiar with. So we have, for example, the benzoyl, which you've come across before when you worked with the Friedel-Crafts acylation. You got the acetyl group with 2 carbons here, and of course the formyl group, and of course the benzyl group. Remind yourself what the benzene looks like. Yeah, here's a carbon right there. Yes. So let's review the preparation of these cells and oxidation, Friedel-Crafts. Well, Friedel-Crafts is the only thing that's quite new to you. Everything else is sort of from organic 1. So if you look at it, say you got oxidation with PCC, this primary alcohol, you get an aldehyde. And here you can see the most I can do with this secondary alcohol is generate a ketone. So here I'm using a strong oxidant, and the best I can do is a ketone. And of course you can do cleavage on the reductive conditions, and you can see that with ketones and aldehydes respectively being generated. Yeah. You can see here, for example, if we have an alkyne, we can go Markovnikov, we can go anti-Markovnikov. And you remind yourself of the Friedel-Crafts acylation that we did a few chapters ago. So, remember, when we have the carbonyl, which is planar, then with a strong nucleophile, what we do is hit it and quench. But with a weak nucleophile, then of course we activate the species by using some sort of Lewis acid like a proton, and then attack with the weak nucleophile. The fate of this tetrahedral intermediate is terribly important to us, whether it's under the basic conditions or the acidic conditions. Yeah. So remind ourselves. Yeah. These are reactions of aldehydes and ketones. You can see that we can get nucleophilic attack or nucleophilic addition, you should say, on the basic conditions or on the acidic conditions. We add an NUH across the double bonds. There's another reaction that we will look at later, and that is the generation of enolates, so the reaction of enolates, where we deprotonate what we now know is a quite acidic proton on the alpha carbon, and that will serve as a nucleophile. So the nucleophilic addition, let's remind ourselves what it looks like. Yeah, and it's done with lithium aluminum hydride and all that lot, those reducing agents, and the alkylating agents, those organometallics, and we can also use nitriles. Yeah, so what we do is quite simply find our nucleophile, hit the electrophilic center of a carbon, and then of course this pops open. You get to the alkoxide, and there's no leaving groups here, and so of course we got to quench. That's what you have with the aldehydes and ketones. So for example, here you have a quite simple question, and it's wondering what species that you would use here. Well, you can see immediately that there's a coupling that took place. There's one carbon added, and it reminds us that the D stands for deuterium. So there's only one reagent that has deuterium in it, of course, and this is this fellow. So it's a really the deuterated methyl grignard, yeah, and then followed by quench. We use ethers as a solvent, the preferred solvent in this case. The cyanohydrin, all you got to do with the cyanohydrin, of course, is attack, because this is a CN minus, so it's quite a decent nucleophile. You'll attack and quench. The importance of the cyanohydrin, which is a coupling reaction, yeah, because it's forming a carbon-carbon bond, is that you can go ahead and you can oxidize to the carboxylic acid, of course, not oxidation, but hydrolysis, yeah. You can hydrolyze, yes, to the acid, or yeah, it's on either basic or acidic conditions, or you can even convert this to a nitrile, yeah, by reduction, and we'll get to that later, to form an amine, my bad. So yeah, reduction to form a primary amine. Well, we'll get to that later. Here you can see there's some there's also different cyanos in nature, so this linamarin, for example, yeah, and here, for example, some species of animal will produce this linamarin, which can then generate acetone cyanohydrin, which is a precursor to cyanide gas. Of course, you can answer this. So herein, we're looking at the acid catalyzed nucleophilic addition, and what we've done is we've protonated the oxygen, and so that has made this carbon more reactive, i.e. we've activated the carbonyl. We're followed by nucleophilic attack, i.e. remind yourself that we got a weak nucleophile, and then there's a few proton transfers. Realize this, yeah, in this case we just proton transfer, we deprotonate, yes, to quench this positive charge on this center here, and we end up with this pseudo alcohol. It's terribly important, yeah, because the fate of this tetrahedral intermediate, yeah, is terribly important to us. So we come to a few named reactions, And we will focus right now on the Wittig, and then later we will look at the imines and enamines, which are nitrogen ligands or nitrogen nucleophiles, and then we'll look at acetals and hemiacetals, which are from oxygen nucleophiles. We'll also look at this biovillager, which is quite interesting, oxygen insertion reaction, and all of these nitrogen species we can look at in a few. Okay, so let's look at the Wittig. Yeah, after I point out this chart to you. So it may look a lot, but it's not, because all it is that we have our carbonyl. So here's our electrophilic center, yeah, and with strong nucleophiles, yeah, powerful nucleophiles like H minus, yeah, all we do is hit and quench, yeah. But with the weaker, so here hits and quench, but with weaker nucleophiles, then something interesting happens, because say for example I get to this amine here, yeah, this amine, and of course I get to this pseudo alcohol species called a carbonylamine, and yeah, it's not very stable, so dehydration takes place. Here for example we have this hemiacetal, which is fairly stable, but again, yeah, under certain conditions we will get to this acetal, and right now we're going to tackle the Wittig, and we have an interesting species called an ylid that we will use. Again, the species that we have is unstable, and so we literally collapse to form an alkene. So the fate of these tetrahedral intermediates, yeah, is the key to these nucleophilic addition reactions. So the Wittig is our first name reaction, and if you look closely, like the Grignard and cyanohydrin, we do have a carbon anide. So it is a fairly strong nucleophile. So it's a basic event. And what we have what's called, and it's this ylid, and it's our Wittig reagent, and of course attack will occur on our electrophilic carbon, i.e. the coupling will result in an alkene. The driving force is the generation of this triphenylphosphine oxide, which is a solid. So it's quite specific, this species, because it won't react with the carbon of esters. Yeah. So of course, given the option, then of course we end up with, yeah, the double bond being formed at the aldehydic species. Same thing here, yes? All right. There's your double bond. So the coupling results in a alkene. And you can see the advantages over stuff we've done in the past, because here, for example, if we want this species, yes, the Hoffman alkene, yeah, if we attack here, for example, with Grignard, followed by quench to give us the alcohol and do the dehydration, then we end up with a Zaitsev as a dominant species and very little of this non-Zaitsev for the Hoffman. So, but with the Wittig, yeah, you can see we have the one carbon coupling species, the one carbon ylid, right? And it ends up giving solely in high yield, almost perfect reaction, yeah, almost stoichiometric. We end up with this Hoffman species. So, of course, we can ask what is going on. The Wittig reaction couples a carbonyl with an alkyl halide to form, of course, a double bond. So, before we move on, let's go through a few nomenclature. An ylide is a species where we have two charged elements, right? Opposite charged elements sitting next door to each other. Do not mix that up with the Zwitter ion, right, or butane, because that is where two different elements, different charges lie in two different parts of the molecule. The ylide, this phosphorane that we're working with, you can see that that there's a resonance structure here, and you can see the charge, the carbonyl nature on that ylide. This ylide is stabilized what we call dp, so there's a D overlapping with a P, pi, so there's pi bonding between them, yes? So it's a dp, so the D orbital is overlapping with a P orbital, yes, on the plane. It's pi back bonding. Why? Because the phosphorus is donating electrons to the carbon, while the filled carbon anion, that lone pair in the p orbital, is donating into the empty d orbital. Back bonding. Remind yourself that phosphorus, of course, is period free, so of course it does have d orbitals available for bonding. The mechanism looks like this. The first thing you got to do is you got to generate your ylide, and we start off with an alkyl halide. Has to be a primary or secondary alkyl halide, because the first step in the production of your ylide is a bimolecular attack by the triphenylphosphine on the alkyl halide. The resulting species has a proton present, which we can use a strong base to deprotonate. So in this case here we have an alkoxide, will deprotonate, and this will form our ylide. So this is the active reagent in our Wittig reaction. Note the bases that you can use. You can use N-butyl lithium, you can use sodium hydride, you can use any alkoxide. The reaction looks like this. You can see that we have here the ylide on the right and the carbonyl on the left. And what I usually think about is square. Let's see how the square comes in. So the coupling will take place here to form your Zwitter ion. Note the square. This phosphorus oxygen is not formed yet, but look, right, there's going to be a oxophosphatane that's formed, so that's your square. But remind yourself that this is unstable. And then you think about the fact that your driving force is going to be the production of this phosphide. So a pericyclic takes place with ejection of that species and your olefin. Can you feel this? Good, let's move on. So here, for example, we have a compound and we want to retrosynthesize it and to see what our starting materials are. And what you can do for us as well as a exercise is give the mechanism yeah, and no, the color of the segment, yes, and think about the halide that we're going to use to generate the ylide. So go ahead and try this, and then we'll go through it during our discussion sessions. To help you along the way, I'll show you the syntons that we're going to be using, and I'll show you the starting materials. Okay, so you go ahead and use those to do your mechanism. Here we have a different flavor of the ylide. Yeah, you can see here we have, it looks like an isopropyl ylide that we're going to react with this propanaldehyde. Think about the number of carbons that you have in the reaction. Think about the coupling, and go ahead and do that. We can go through that in our discussion sessions. Here is another example. Now we have the alkene, and we want to know which one of these sets of starting materials did we use for the alkene. So your disconnect is here. Yeah, so go ahead and see if you can put that together, and we'll also go through this during our sessions. So ylides do exist in biochemistries, and herein when you get back and we discuss this, I'll show you the role that the thiazole ylide plays in thiamine, which is vitamin B1. Yeah? We'll want you to think about why is it that this is stable, or what stabilizes this thiazole ylide. Look at the carbon and ion next door to this positively charged nitrogen. And so this will end this part of the lecture. We'll continue with the nitrogen ligands, nitrogen nucleophiles when we get back for part 2.